Good afternoon, everyone. It's a great pleasure to have Dr. Jamal Zeinalov, who is the co-founder and CEO of Atomic Works. And this is the first of the industry seminar series that we have launched at WIN, and hopefully more will be coming in near future. Atomic Works is a software development company specializing in simulation platforms for nanomaterials. He has over 15 years of experience in scientific and engineering simulation software development and holds a doctorate degree in aerospace engineering. Of course not from Waterloo, but we will not hold it against you.
Sorry, guys.
We don't have the aerospace engineering program yet. The goal of Atomic Works is to introduce molecular simulation tools to the widest possible audience of researchers, scientists like you, and engineers working on nanomaterials, research, development across different fields. And in WIN, we have really a wide variety of various applications. And we really welcome you here. And Jamal, we look forward to this talk and more interaction with our community as well.
Absolutely. Thank you so much. So, hi, everyone. My name is Jamal. I'm here to talk to you guys to tell you a little bit about our company, where Atomic Works. You could technically probably still classify us as a startup. We're 3 years old. We've been developing this project for about 2.5 years. We're a small team of scientists, computer scientists, physicists, chemists, and I'm an odd one out. I'm the aerospace engineer. It's a long story how I got into this. But I'll tell you a little bit about our software, what we do, how we do it, and also what we're hoping to do in the future. And hopefully see if we can find some collaboration opportunities or maybe some interest from you guys to try out our software as well. Okay, so this is kind of, I want to go over kind of our philosophy a little bit about how we've came up with the idea of the software, what's behind it, what was the driving force, and where we're going with it. This came out largely from my own PhD research, which I was doing in material sciences, on characterizations of metals on nanomaterial scale. And what I found out using the tools that are there right now, as I'm sure a lot of you have found out, is A, they're not very approachable. So you got to spend a fair bit of time getting into it. You know, a lot of trial and error, a lot of, trying things out before things actually work. There's really no one good tool to go from the beginning to the end of the simulation. So preparation is done in one place, simulation is run in another, post-processing is done somewhere else. Again, not kind of the best, most optimal approach. And they're really usually built for one purpose in mind. Now, there are some more general simulation softwares out there, but usually just because of the nature of nanomaterials and the world we occupy, you kind of have a whole bunch of very specialist softwares, each one built for a specific mission or an application. So our goal was threefold here. We wanted to build a very flexible QM-MM-MC. So starting from like DFT, ab initio type of methodology, all the way to molecular dynamics, and then all the way to Monte Carlo probabilistic types of simulations. We wanted to combine these three major methodologies within one simulation space. That was kind of one. Make it flexible enough that you could actually apply it to different applications, different fields of research. And also hybridize it in a sense that you would be able to use all three of these methodologies within the same simulation space. And I'll talk more about how we go around achieving that. We also wanted to kind of make it more accessible for researchers, for scientists, for engineers, for students, for people who are just getting into it, for people who have been in this field for 20 years. Make this more accessible. And in that, we looked at kind of more towards engineering, because the engineering field in general has a lot of mature and kind of great commercial type software where you can get into it fairly easily. It gives you the results that you want, and you spend a little time as possible learning the tool, making mistakes with the tool, and also setting up your problem. You're really spending your time analyzing what it is that you see. And last but not least, we wanted to make it kind of like a discovery sandbox. If you're familiar with a software like COMSOL, I think people have compared it to that too. It's kind of like that. You kind of can define your own physical parameters, characteristics, interaction methodologies, and this goes and solves it for you. So it's not limited to just one field, for example. So the way that this kind of the flow of the software kind of works, just to give you a very high-end overview, we borrowed, again, a page from engineering types of software. And the first thing we developed was a CAD module. So this is a CAD module where you can define topology of the parts you're going to be using. And this is great because it's parametric, so you can do optimization. You can look at how different topologies are better or worse for the particular problem you're trying to solve. So we have a module where you basically do your entire sample preparation. You do it all in one place. It's very visual. There's a lot of visual feedback. It's very easy to use. There's not a lot of typing. You don't need to know any programming to start using this. It's all has been made as user-friendly as possible. After that, you go to the molecular definition. So again, you define the molecules you're going to be solving. You define the layout. You define how they interact with each other. All that done is, again, within the same software. And I'll show you later on just how easy it is to use it. The correlations that we have, so again, we allow people to use anything from ab initio, DFT type of basis sets, definitions to EAMs, MDs, semi-empiricals, Monte Carlo simulation setups. You can use those individually, of course, or you can combine them within the same simulation space. We have included a bunch of boundary conditions. Now, this is something we hope to grow through research partnerships with scientists like yourselves. Right now, we have structural, thermal, and some electromagnetic boundary conditions and interactions that you could set up, but we want to grow that list as well. Then, of course, you've defined all of your sample. You're ready to go. It's when the solver comes in. So the solver has been made. It's, of course, parallelized. You can run it on a supercluster, but we've also made it such that if the problem is small enough, you can run it on your laptop. If you want to just do a quick check of something, you can also set it up that way that you just run it quickly on your machine to see if things are working or not. And you can, as I said, it's a hybrid solver, so you can have multiple different methodologies running within the same simulation space. And then post-processing. So you don't have to go anywhere else. You get your simulation results out. You can view them within the same software. You can plot things. You can look at your results. You can, again, there's a lot of visual feedback. That was kind of the big point here. And you can basically finish your job from the beginning to the end, not leaving the software package. So that was kind of one of the biggest, driving factors behind developing the software. So the CAD module, as I said, you can define many different types of topologies. We've kept in mind that we're dealing with nanomaterials here, so you could specifically define 2D or 3D structures or 1D structures like CNTs. You can combine volumetric geometries together to create very funky, different topologies. Everything is parametric, so it is optimizable. So you could actually set up an optimizer outside the loop to go and change change the way that the problem is set up, change your topology, run it again, see what kind of optimized results you might get. Okay. The molecular editor, again, it's included within the software, and it's the biggest thing that we kind of thought about when doing this is, I know I had to deal with it a lot when I was using tools that are available out there right now, is you define a molecular structure via a text file, for example, right? It's an error-prone method. If you're not very familiar with it, it's going to be a while before you kind of figure out how to do this. And you're going to spend time that you really shouldn't setting up a model. Right? This way, there's a lot of visual feedback. All you need to do is set up your molecular structure, and then there's a lot of flexibility in terms of how you define it, in terms of how you copy things, in terms of how they then get applied to the model. And the way that the definitions are done in terms of the propagation of the material within the topology is we based it on the crystallography definitions of screw axes and glide planes. So you define those, and that basically tells you how does this crystal propagate throughout the material. Again, fairly straightforward. The boundary conditions, as I said, there's electromagnetic field boundaries you can define. You can also look at the structural boundary conditions. So as I said, it kind of came out of the research into structural properties of metals. So that's why structural is probably the most developed boundary condition set that we have at the moment. But there's others as well. There's thermodynamic boundary conditions. You can simulate material deposition or printing through the source boundary condition. So you define a point in space, that point can move. And you can tell the simulation, now start adding material from this point, and it will do that for you. It will generate materials for you, so you can simulate printing on molecular scale as well. And then repeat boundary conditions for those large simulations where you just can't fit it into the simulation domain, but you know that it is periodic, so you can apply that as well. Now, in terms of correlations is what we basically call any kind of material interactions, be that DFT, EAMs, MC, whatever you can think of. We included those here. And you can go very simplistic. For example, you can just define an interaction between two atoms based on a distance, and that's it. And that's all you're calculating. You can do as simple as that to all the way to defining the basis sets for local density approximations. And you're at the very other end of the scale of the complexity in terms of calculations. And the way we combine those two methodologies or more methodologies together is we ask you to define energy barriers, so energy levels. If within a simulation space, a certain subspace becomes very energized, very energetic, a DFT calculation is going to be performed just on that subspace. Everywhere else, for example, you'll still do MD. And that subspace moves depending on the energy levels within the system. And then there is a boundary condition between the two where both methods are used to calculate the properties of the materials, and that's how the information is exchanged across the boundary. So that's the basic idea behind it. And the reason that we wanted to do it that way is in order to expand the simulation space, but still maintain integrity, still maintain the accuracy of the results. This is one of the ways of doing it. In the subspace of your large domain where interesting stuff is going on, maybe there's a chemical reaction, maybe there's a crack propagation going on, you do DFT. You do something that requires a lot of computational intensity. You go outside of that domain, you're still simulating that, but now you can spend a lot less resources, computational resources, but still get fairly accurate results there as well. Right, so that's the way we break that down. Okay. Now, one of the other ways that you can speed up the simulations that we included it, so let's say you want to stay within the same kind of methodology domain. You just want to do DFTs, you just want to do MDs or MCs. The other way you can speed it up is you can do the same kind of thing. You can chunk up your space into different subsections. And depending on, again, we'll look at it from the energy point of view, either potential or kinetic. Usually kinetic in this case, if it's an MD type of simulation. But regions of space that very high kinetic energy would get recalculated much more often than the regions of space with smaller kinetic energy. So again, this is just increasing the size simulation or increasing the fidelity of simulation without really giving up anything in return. You're just, the way you're recalculating the properties of the materials is just optimized. That's all. And it's optimized, it gets recalculated step by step by step. Okay. So to tell you a little bit about our solver architecture, this is kind of standard for commercial products, I guess. It's a client-server interface, so you could have your client, which is the UI, the way you interact with the software. You can have it on your laptop. You could have it on the desktop. It could be installed at the supercomputing lab itself. And then the server could really be anywhere in the world. Could be in the same place, could be on the supercomputing clusters, could be on the cloud. If you set up, you can spin up a job on Amazon AWS service and you can solve it there. So the idea is you can log into your server as it's running anywhere in the world, check up on your results, import the results from there. One of the things we added to it, and it's kind of prevalent for large research groups where multiple people need to look at the stuff at the same time, we do support multiple clients looking in on the same job at the same time. So it's kind of a need for that kind of interaction. Okay. So once you're done doing the simulation, the post-processing. We find that also to be one of the more challenging aspects of the tools that are available. Basically, what usually happens is, with the exception of one or two products that have actually gone their own post-processor, someone will write a post-processor independently of the company that originally made the solver. And they will read in the results, and you can kind of view it that way. We kind of thought that was a little bit of a disconnect to do that. If one updates and the other one doesn't, you always run into problems like that. So everything is done within the same simulation space. While the simulation is running, you can start viewing the results. So right away, things are available to you. So you can start looking at it right away. The watchword, as you can probably guess from all of this, is user interaction, user comfort. Are people more likely to keep using the software? Is it nice to use? It's kind of oriented towards that. And then some of the applications that we looked at. So we conceived of this product as a general product. So we're not attacking any single one area of nanotech as wide as it is individually. And in that, we're kind of relying on the researchers that we work with to take the tool and to validate it within their individual field. We have done some work on it, but it's basically a very small demo to show people that it works. But we do rely on the researchers, our partner researchers, to take the tool, apply it to their research, and a lot of times give us feedback to say, hey, this is not working, or we want to add these features to make sure that it works the way it's supposed to. So we've started, obviously, with metallic compounds, as I said. There's CNTs and graphene that we do. There's research going on quantum dots using the software right now. We're also looking to get into the power storage and battery design. So if any of you guys are interested in that, we are very much interested in trying out our software in that field. And we think it would be successful there as well. And also plastics. And one particular thing about plastics that we find talking to the companies out there who are looking at this tool is they're looking at the scale. They need to increase the scale of the simulation in order to better kind of simulate what is going on in their manufacturing processes. They find that very small scale that right now molecular dynamics tools in general are limited to are not well enough to describe what's going on during the manufacturing process. So they've asked us to look at a ways of expanding the simulation space while keeping the computational requirements the same. And hybridization of different methods is one way of doing it. The other one is the subdomain of time calculations that I've described. That's another approach that we've taken. So for metals, we do a lot of different simulations. We do grain boundary interactions. That was kind of the first specialization of this tool. It's very easy to set up different metallic crystals with different boundaries close to each other, interacting, and then observe what is going on. So for example, if you wanted to look at crack propagations across boundary level, you could kind of do that here. You can take a look at that. Void formations, clustering, the migration, the energy minimization problems are very well suited for what we do. And just in general, any molecular dynamics simulation software would do the same. And then thermal and mechanical properties as well. So that was kind of the first application, as I said, of the software. We've started looking at the CNTs and graphene. At the same time, we started looking at the batteries and power storage units. So this is only one of the kind of 2D applications we're looking at. We are looking to expand into other two-dimensional applications, and the software has been specifically defined so that it's very easy for you to define these layers, these scales. So one of the things that are available to you in the CAD module is a layer type of tool where it's very easy for you to set up lots and lots of these layers in different configurations and different sizes and different things. Okay. Quantum dots, in this case, we're working with the researchers who are focusing on a kind of lowest energy configuration of a certain quantum dot configuration. So the way that we do that is if you define a molecular structure, you want to find out what's the actual lowest energy configuration of the structure. The software can do that by setting up a certain statistical ensemble where you're continuously taking out the energy from the simulation as it goes, collapses into lowest energy form. And then the nice thing about that is we've made it possible so that once you have that configuration, you can save that as a molecule. So now you save that as your beginning of your next simulation. You kind of know that you have saved that the least energy, the most energy efficient, I guess, form of that molecule. And then I said power storage, so we're looking at, we're looking at lithium ion, but also we're looking at more unconventional materials. I guess graphene, I can't really say it's now unconventional for this type of application. People have been starting to use it. But other unconventional materials, 2D and both 3D, we're looking at the power storage, the power capacity, recharge rates, thermal profiles, chemical reaction pathways, and so on. And the other area we're kind of looking at is, again, plastics. And as I said here, we're mainly looking at scale increase. So we want to increase the scale as much as possible while still simulating the formation processes as well. One of the things that we kind of actually had to do in conjunction with that is when you go beyond something like 50, 60,000 particles, 100,000 particles, 200,000 particles, million particles, it becomes very hard to actually look at it. A lot of software out there can't really handle that many things on the screen at the same time, independently changing as you're progressing through your time steps. So a lot of research was actually done in terms of what do we do? How do we throw out 100,000, 200, 300,000 particles on the screen at the same time without you waiting for a couple of minutes for the next frame to appear, right? And we've done a lot of progress in that, where now it's just a few seconds, maybe for something like 100, 200,000 particles for the screen to update and show you more stuff. And we've actually used a game engine for our UI. So when we were developing our UI, we developed it with Unity. Game engines are very good and efficient at throwing up a lot of things on the screen at the same time and also having a high frame rate of change. So this is what we've used to actually power our UI, to be able to show as much as possible as we can on the screen at the same time. Okay. So kind of some of the things that are next for us in our future. We're going to be improving the hybridization, as I said before. We have a QM and MM hybridization in right now. The MC is not integrated in with it yet. It's going to be integrated next. That's what we're looking for this summer. We're going to be doing more optimization and machine learning modules. So we've partnered together with IBM, and we're going to be using Watson to actually be the machine learning algorithm behind the software. So the idea there is you run the simulation 100, 200 times. It starts learning. It starts suggesting to you now what the topology that you should look at next. Eventually, it's going to start suggesting molecular configurations, elements, things like that, that maybe you haven't thought of, but it maybe have noticed in other runs or the runs that it's been doing. So we're going to be working in that direction. So that's hopefully it's going to, alpha version of that is going to hopefully come out this year, and we'll be able to give it to people to start playing with. We're looking to create a large proof of concept library. So this is kind of for those of you maybe who are interested in starting your own companies kind of thing and progressing that way in the space. What we found is in software sales especially, but I'm sure this is true for other industries as well, the way you do it is you build up the trust over a few months where you can show them that your product does meet their specifications. And one way of doing that is you need to have a proof of concept library where you've worked with researchers before, they've used your tool in their research, they maybe have published a paper or two using it, and now you can kind of show other people that this kind of process can be simulated using your tool. We're working on the Gpgpu support, so that's another way of reducing computational costs while either maintaining or expanding the design space you're looking at. The molecular dynamic simulations are particularly well suited for Gpgpus. And there are software packages that do MDs out there that use Gpgpus, obviously. One drawback there is, although we're confident it will speed up the calculations, is that in general, they're not very accessible. There's not a lot of GPU clusters right now in Canada that, for example, you guys can access to run this. There are a few. There's one in Sinet that's just been installed. But in general, they're much more rare than your typical computational clusters that are all across everywhere. But if you do have access to those, it's a great resource to run these type of softwares. In general, there are several-fold at least increases in terms of speed and fidelity of the results. And then this is more of a kind of like a Hail Mary long-term solution. When we go and look at when we talk to our customers, one of the things that they always push for is larger, right? You need to simulate more. Otherwise, we're not getting accurate enough results. And DFTs being what they are, computationally intensive as they are, there's really so much you can squeeze out of it. So the quantum computing is kind of what we see on our horizon as the next step to tackle. To actually write MD, DFT type of simulation methodologies within the quantum computing paradigm and see what kind of, if it's a revolutionary shift or if it's an incremental shift, we don't know yet. We'll have to see once we start working on that. Let's see. And also, what we're looking for. Of course, we're looking for customers, people who will use our software to help them develop their products. But we're also looking for research partners. So we do work with several universities to help us develop the product further. And we're hoping we'll walk away from here, again, having a few more contacts as potential research partnerships. And of course, collaborations. So as I said, for example, we work with IBM to, where we collaborate, where we take Watson and we customize it for our purposes. So in the end, our software has more capabilities, and IBM will also have customers for Watson because they're the ones who are licensing it. So that's kind of another avenue of approach that we're looking at. I think what we'll do is, we have time. I'm going to show you guys a brief kind of way the software works so you can kind of appreciate the what we've done. We're not going to do anything too crazy today because I'm running everything on my laptop, including the server, so we're not going to do GFTs today. But I'll kind of walk you through maybe a simple application and just show you the flexibility of the software. So this is what you see when you start up. Sorry. So I can also see the screen. Okay, 1 sec. Let's restart the screen. There we go. Okay, so it's made with Unity. You see that? Okay, so here is where one of the first things you will see is this is where you log into the server. Now everything is on the same machine, so it's going to be fairly fast. But this is the mechanism you use to log into any server around the world, basically, to view your results. Then there is the loading screen for compounds and correlations. Those come predefined from us, but you can also define them yourself. Let's do a quick test 3. Great. So the first thing, as I said, is you define your topology. So in this case, let's do something a little funky. Let's do a cuboid. All the units are in, the dimensional units are in angstrom, by the way. So something like that. And maybe we'll put a cylinder through it just so I can show you what it can do. So we'll do difference here. And we'll make it, I don't know, something like that. And then you can just do calculation. And you have something interesting looking like that. So it's very fast for you to create different topologies using this tool. You can, your imagination is your limit, basically, whatever it is that you want to do. The next thing we're going to do is we're going to go back here and we're going to set up the material we want to populate it with. So that takes us to a molecular editor. So what we do here is you use these to define the molecular units that you want to do. So in this case, we just have an aluminum and an FCC structure. It's a lot of visual feedback, as you can see. So you can just populate your elements here. You can see where they are. You will set up this, in this case, it's screw axes to tell it how to propagate the material. So again, this is very straightforward. And you just apply it. Okay. Okay. And now we asked to mesh the material. So it's going to go calculate the material propagation through this geometry that we've set up, and we're going to get some results. So let's hide the geometry for a minute. Aluminum. And there you go. This is what you have. Now, because this is a very small simulation, let's actually go and look at it as kind of detailed instead of a simplified view. So there's a couple of ways of looking at things. Once you've set that up, you can define your boundary conditions, or you can just go straight to the solver, and you can load your correlations. So these are correlations defined for EAM interactions. So we have density and potential, distance density and distance potential, but you can just do, for example, distance potential and just do simple particle-to-particle interaction without looking at densities at all. So it's up to you. This is what I mean by kind of a sandbox method. You can add these, you can modify these, you can come up with your own relations and see, what kind of results you can get. So for now, let's just add these guys here. And on the very basic level where we're ready, we're just going to run this. We're going to run it for 100 femtoseconds at a 10 femtosecond intervals. And while it's calculating, which is going to be very fast, we'll just quickly set up our results view. So you can, for example, I don't know, let's look at the potential energy that we're going to calculate. So the first step is done. We can go there and look at the potential. Yeah, so we can look at the potential energy right away. Right, so you can change your results, you can look at them, and so on. So that's kind of the idea behind this, is you can take this from the beginning to the end within the same simulation software without going anywhere else, without switching to anything else. Right. So as I said, I'm very excited to be here today because I met already several researchers today who I hope will have further conversation on this tool. And we're hoping to develop more relationship with the University of Waterloo and the researchers here to help us further develop our tool. We're a small team. We're 4 people, including myself. We're based out of Mississauga, so just an hour out of here. So anytime you guys want to maybe visit us, you're welcome to do so, or we can come up here to give you a more thorough demo if you wanted to of the product as well. Okay. I think that's it for me. If you guys have any questions, please. Repeat them in the mic. Okay.
Yeah. Any questions? Yes.
I am a student for computational chemistry field, and I have a few questions about the algorithm to apply. You said you use a hybridization of molecular dynamics and density functional theory. I just don't fully understand how does it work. Like you said, some part of the molecule has more complexity and you want to make high accuracy. The other part you just use less accuracy method. But how can you decide which part is important, and can the interaction always be localized?
Okay. So the question is, how do we combine different methodologies together within the same simulation space, and how do we kind of decide which part is going to be DFT, which part is going to be MD, or some other method? The primary way we're doing right now is through energy, so either potential or kinetic energy. So you set up several barriers that you will basically telling the program, anything above this energy level, use DFT. Anything below this energy level, use MD. Now, between those 2 levels, at the boundary condition, we have a certain boundary layer where both methods are used, and then we'll look at the results for that boundary level, and it's an average methodology. Kind of, we're taking an average, a weighted average of both methods, and that's how you actually transfer the information from one method to another through this boundary condition. That's how that's done. We're doing that right now. So how does it compare in terms of to other packages, in terms of accuracy of results? We're working on that right now. So we're going to be probably releasing this information in the form of videos. That's how we like to communicate. So on our website, we'll post videos. We're going to be posting them a lot, and one of those would be comparisons. So we're going to be comparing our software to other packages.
Another question is, you said you are going to implement some machine learning algorithm. But as for me, if you want to do this, you need to first have a large database of systems, and how can you get this database?
So the question is now, if you're going to using machine learning algorithm, which it does need a large database of results, how are we going to do that? The idea is, yeah, out of the box you won't be able to use it because that algorithm is not going to know anything. The idea is, as we're developing it, as we're developing machine learning algorithm, we're training it as we're developing it. So there's going to be some things, some areas where it's going to have more expertise than others. Those are the ones we're going to train it in. But I would say for something new, if you want to apply it, you would have to run hundreds, thousands of simulations before it can actually learn from it. So the idea is, yeah, you will have to first pre-train the machine learning algorithm before it can help you. Yeah, that's true. We're fine with that now. You're getting into IP issues here, right? So for some companies, it's going to be a no. For some researchers, it's going to be a no. It's going to depend on individual research groups and individuals who are using it. If people are willing to share, that would be great. That would be the way to go, yeah. Yep.
Okay, then I would like to ask you, you mentioned about IP problem, but my question is more general. So how do you enforce security? Because that data that is transmitted to server and back, I would say, like in many cases, it would be highly sensitive. So could you please highlight some of this question?
We're not, let's put it this way, we're not a security company. So the way we approach this problem is we're going to put in a minimum stuff in, like password protections and stuff. Someone intercepts it. We rely on the users themselves to set that up if that's important to them. So for example, companies would have either their own supercomputer behind their firewall completely, so nothing gets out. That's how a lot of companies actually approach that issue. Sometimes if they are working with someone like Signet, so they have an external connection, they'd usually ask for an encryption. Again, we're not going to do anything like that here because that's kind of outside the scope of what we're trying to do. So we will disclose to, I guess, the users of our software the dangers that are possible. Yes, it's a sensitive information, you should protect it, but it's really their job to protect it. Yep.
I was also going to ask about security.
Yep. Yeah. Lots of security questions, okay.
Since maybe others are thinking, I have a question. So the examples and some of the problems that you talked
Yep.
about is more on bulk materials.
Yep.
What about interface? Say, for example, if I'm bringing two, van der Waal heteromaterials together,
Yes.
can I work on those interface signs and try to find new, maybe electronic charge density fluctuations and things like
Yep.
that?
So in terms of working with boundary conditions and boundary materials, those will depend on the DFT methodologies you use. So one of the things that we did is we've added a lot of DFT methods already pre-built, but you can also define your own, or if you find something in the literature that it's not there, it's very easy to input that here. So if there's a particular DFT methodology or group of calculations that you would want to use, you will just define them within the software and use them that way. Yeah.
So
That
it's
can be done as well. It is possible to do that as well, yeah. Yeah.
Any other questions of this? Maybe then last. Yeah, please.
Okay, thank you very much for the talk, and I have one question. Is it possible to apply your program for big periodic solid-state structures?
For applying this for the big periodic solid-state structure, so there's a couple of things that we introduced that help with that. One is the periodic boundary conditions. So you can set it up such that if you're doing a bulk simulation, you can set up periodic boundary structures that will propagate. So that helps you certainly. And then beyond that, it's just the methodology you use. That's what's going to drive your computational costs. But it is possible to scale it as much as you can. I would say you're not really, from what we've seen in our tests, you're not really limited by the number of cores you have at your disposal. That can grow as much as you want, and this will scale with it. You're more limited by the memory. So if you have a large number of cores, large simulation space, you really need also a lot of memory to process and to store that data at the same time. Yeah.
You have plans to have some part of your product as a free version for students and researchers?
So in terms of having a free version of the product, so we are a company, we are a commercial enterprise. We do receive some funding from the government, but mostly it's our money, and we had to raise money as well. So we are looking at a commercial angle first and foremost. We are certainly going to make it a discounted version for academic world. And one of the things that we actually want to encourage this to be used as a teaching tool because it's extremely visual. So if if a professor, if you guys are teaching an undergrad course, for example, this can be extremely helpful in showing people the molecular structures, the interactions, and so on. There's no plan to make a free one at this point, probably, but maybe a discounted one. Yeah. So you can have, So how do we deal with exchange and correlation interactions, right? So how do we implement that? It's part of the inputs as well that user can define. So there's a lot of different XC, methodologies and definitions out there. We have predefined some within the software. You can define additional ones yourself. In general, we're limited to LDA and GGA. So those are the two main DFT methodologies that we're looking at. We're not looking at anything more fancy at this moment. And really, if you're doing a large system, you're kind of limited to those two. Anything more accurate and more computationally intensive, you're limited to much smaller system. In terms of using those two, there's Gaussian and Slater basis sets that you could use as well. But in terms of XCs that we use, there's predefined ones and there's additional ones you can define. It's kind of like we're not ourselves DFT developers. We don't come up with new methodologies of doing DFT. We look at the literature out there, the methods that have been proven to work, that are available to the public, and we kind of put them in. So it's almost also up to the researcher to see what kind of exchange and correlation interactions they want to use, and then either use one of the pre-built ones or input one themselves if they want to use a different one. Yeah.
Yes, more other questions
Yeah.
that flowed into your email and
Yep.
things. So
Absolutely.
thank you so much, Jamal. Really appreciate
Thank
it.
you so much.
It was very informative. And a lot of the students are here, grad students, so hopefully they will start using this.
Absolutely.
As well.
Absolutely.
Okay.
So you guys know that's the contact you can use. If you guys want to come and talk to me, I can give you my card afterwards. You can reach me directly as well. Okay. Thank you so much.
Thank you.
Thank you.